Hello my dear student, welcome to EPG Pathshala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hindu University, Varanasi. Today we are going to talk on module Semiconducting and Oxide Nanowires under the paper Nanoscience and Technology 2. After completing this module, my dear student, you are able to learn about one-dimensional semiconductor nanowire. You will also learn one-dimensional oxide nanowire, different types of nanowires and their application, along with the growth. You will also learn the experimental techniques for synthesizing this material. A nanowire is a nanostructure with a diameter of the order of nanometer, means 10 to the power minus 9 meter. It can be also defined as the ratio of the length to width being greater than 1000. Nanowire can also be defined as the structure that have thickness or diameter constrained to tens of nanometer or less and an unconstrained length. This kind of nanostructure is also known as quantum wire because at this scale quantum mechanical effect becomes important. Nanowires show many interesting properties which are missing in three-dimensional bulk materials. The interesting phenomena arises due to quantum confinement of electron, which lead to discrete energy levels that are different from the traditional continuum of energy levels or band found in bulk materials. The quantum confinement exhibited by certain nanowire manifest themselves in discrete value of electrical conductance. Such discrete values arises from quantum mechanical restraint on the number of electrons that can travel through the wire at the nanometer scale. These discrete values are generally referred as the quantum conductance and are integral multiple of each 2e square by h, which is around 77.41 microsecond. They are inverse of the well-known resistance unit h by e square, which is roughly equal to 25812 ohms and referred to as von Klitzing constant Rk, where I want to discuss the quantum confinement of one-dimensional nanowire. What is nanowire? So, to discuss it, when the size of the dimension of a material is continuously reduced from a large or a macroscopic size such as meter or a centimeter to a very small size, the property remains the same at first. Then small changes begin to occur. until finally when the size drops below 100 nanometer, a dramatic changes in the property can occur. As discussed in my earlier lecture, one dimension is reduced to the nano range while the other two dimensions remain large. Then we obtained a structure known as two-dimensional material or a quantum well. If two-dimensional are reduced to a nanometer range and one remains large, the resulting structure is referred as one-dimensional material or quantum wire, which is the case in this particular module. If all the three dimensions are reduced in nanometer range, is called zero-dimension material or quantum dot. The word quantum is associated with these three types of nanostructures because the changes in the property arises from the quantum mechanical nature of physics in the domain of ultra small. The process of diminishing the size has been illustrated in the figure very clearly. Quantum size effect in nanowire will have an impact on electronics and photonics applications. Quantum confinement occurs when the nanomaterial dimensions approaches the size of an exciton in bulk crystal called exciton Bohr radius. This leads to an increase in the band gap with a decrease in size of the nanomaterial. Keeping this in view of the importance of 1D nanomaterials, in this module we are interested to study one-dimensional nanostructure material which we can call 1D NSMS or quantum wire. I want to discuss the example of silicon nanowire. They are some semiconducting nature, dear student. There are many different type of nanowires such as superconducting YbCO, yttrium, barium, copper oxide, metallic, for example nickel, platinum, gold, semiconducting silicon nanowire, indium phosphide, gallium nitride nanowires, and insulating, which is silicon oxide or titanium dioxide nanowires. Molecular nanowires are composed of repeating molecular unit, either organic, for example DNA, or inorganic, where MO6S9XIX, which is inorganic in nature. First, I will discuss the semiconducting nanowire. The nanowires are the great interest due to their potential application in electronics, optoelectronics, and sensor application. In this class of nanowire, silicon nanowire have received the most attention due to the historical role of silicon in the integrated circuit industry. Continued high performance from silicon may require alternative to thin film based planar CMOS transistor in the form of novel devices, three-dimensional structure, innovative architectures, and integration with other functional components. Silicon nanowires are frequently studied towards applications including photovoltaic, nanowire batteries, thermoelectrics, and non-volatile memories. Silicon nanowire, also referred as silicon SiNWS are a type of nanowire most often formed from a silicon precursor by etching of a solid or through catalyzed growth from a vapor or liquid phase technique. A large number of techniques exist to fabricate silicon nanowire. These can be classified into bottom-up and top-down fabrication technique, which is clearly shown in the figure. In top-down fabrication, the lithography is used to define the fabricated structure that is then transferred from photoresist to the substrate by etching or a similar way of structuring the already available material. In the bottom-up approach, the material is added to the substrate in a self-organized way. So these are the two techniques by which researcher can fabricate silicon nanowire. Here I will discuss another example of semiconducting nanowire, which is germanium nanowire. Germanium is an important semiconductor with a direct band gap of 0.8 electron volt and an indirect band gap of 0.66 electron volt. It has been receiving much attention recently, either as a pure element or as an alloy with silicon for logic and other devices. Germanium offers higher intrinsic carrier mobility than silicon. The mobility is of 3900 for electron. However, for holes it is 1900 centimeter square per volt second versus 1500 and 450 centimeter square per volt second at room temperature, enabling faster switching and higher frequency devices. Other advantages includes high intrinsic carrier concentration, which is 2.4 into 10 power 13 centimeter minus 3 versus 1.45 into 10 power 10 centimeter minus 3. Larger bulk excitonic Bohr radius 24.3 nanometer versus 4.7 nanometer for more prominent quantum confinement effect even at larger material dimension, and compatibility with high K dielectrics, enabling integration to current semiconductor processing technology. Germanium is also compatible with third, fifth material. For example, good lattice matching with gallium arsenide. Germanium oxide exhibit interesting optical properties suitable for interesting integrated optoelectronic circuit. All these features have prompted extensive investigation of germanium nanowire growth, characterization and application development. In figure, scanning electron microscope images on as made germanium nanowires. The scale bar correspond to 4 micrometer has been shown in the figure B. Some images of germanium wires after vacuum thermal treatment has been shown. In this case, the scale bar correspond to 1 micrometer. I want to discuss 3-5 kind nanowire, which is semiconducting in nature. Group 3-5 compound that are semiconductor materials are of great interest in electronics and optoelectronics for applications in high power and high frequency transistors, light emitting diode, lasers, resonant tunneling diodes, solar cells, photodetectors, and others. Their usefulness in the above application have been well established in the last 2 decades through thin film and quantum well of gallium arsenide, aluminum gallium arsenide, indium gallium arsenide, indium phosphide, and GAP, etc. Let us talk about gallium arsenide nanowire. Gallium arsenide nanowire is shown in figure A, is a direct band gap semiconductor with a band gap of 1.42 electron volt. Electron saturation velocity of 10 to the power 7 centimeter per second and carrier mobility of the order of 8,500 and 450 centimeter square per volt second for electrons and hole respectively. It has been grown in the nanowire form by laser assisted catalytic growth, molecular beam epitaxy, MOCVD, and template guided approach. These techniques will be discussed in detail in coming slides. Let us talk indium arsenide nanowire. Indium arsenide, another example of group 3-5 compound, exhibit a small energy band gap 0.35 eV, high electron mobility which is around 33,000 centimeter square volt second, and a large quantum confinement energy. There have been several reports on the preparation of indium arsenide nanowires. Indium arsenide growth by MOCVD with a thin layer of silicon oxide serving as catalyst on indium phosphide of 111 direction or indium arsenide 001 crystal direction and silicon 001 kind of direction of the substrate. Figure B shows scanning electron micrograph images of indium arsenide nanowire on indium phosphide substrate at temperature 540 degrees Celsius in between 660 degrees Celsius. Now let us talk another nanowire which is indium phosphide. Indium phosphide, another example of 3rd-5th compound, is a direct band gap semiconductor with a gap of 1.34 electron volt that has been widely investigated and used for electronics and optoelectronics applications. It has been grown in the form of nanowire using laser assisted growth, sublimation of indium phosphide powder, molecular beam epitaxy method, and MOCVD, etc. Figure C shows the results of indium phosphide nanowire synthesized using MOCVD technique, which provides vertical uniform diameter nanowire. Let us discuss 3-5 nanowire of gallium phosphide. Gallium phosphide is a wide band gap semiconductor with an indirect gap of 2.26 electron volt. The electron mobility of bulk gallium phosphide is 160 centimeter square per volt second. Gallium phosphide is preferred for high temperature electronic applications and light emission in the visible range. In laser catalytic growth of gallium phosphide, a gallium phosphide solid target is laser ablated to provide the source of vapor, and the use of gold colloids appears to provide a tight diameter distribution of grown nanowires. In general, the mean nanowire diameter is only 1 to 2 nanometer larger than that of colloidals. Sublimation of gallium phosphide powder has also been used to generate the vapor source. Schematic of laser ablation growth, well-defined gallium phosphide nanowire and monodisperse gold colloids as a catalyst has been shown in figure A. Scanning electron microscopy image of a typical array of gallium phosphide nanowire. I want to discuss another class of nanowires, which is oxide nanowires. Metal oxides are an important class of materials that find application in wide variety of fields. For example, zinc oxide is an direct wide bandgap semiconductor with application in ultraviolet and near UV photonics. Many metal oxide find application either as a catalyst supports or active catalyst material and conducting channels in gas sensor. Several metal oxide also find direct application in electrochemical energy devices such as lithium-ion batteries, electrode materials, and solar cells. Almost all of the above application can benefit from the availability of metal oxide in the form of nanowire due to various reasons. Well-defined crystallinity and surface reactivity, electronic properties, high surface area. In some cases, metal oxide nanowire with diameter less than few nanometer are sought for understanding the quantum confinement effects. Even though nanowires will with radius larger than corresponding Bohr radius may not show distinct properties compared to bulk, they are still promising due to the following reasons: that fast charge transport, low threshold for percolation, high surface area, and well-defined crystal surfaces. The above mentioned applications are diverse and require metal oxide nanowire in different formats ranging from epitaxial nanowire array, vertical nanowire array, or a variety of conducting substrates, networked thin film, highly dense thick films, and powders. For epitaxial nanowire array, there should be a minimal lattice mismatch between the nucleating metal oxide crystal and the underlying single crystal substrate. For vertical nanowire array, high nuclear density are typically necessary. Several synthesis methodologies are available for the growth of oxide nanowires. Particularly, four important vapor phase methodology used for their synthesis and mentioned here. The first one is the foreign metal catalyst assisted growth. The second one, direct oxidation of large molten metal droplets. The third one, direct chemical vapor transport or chemical vapor deposition. And the fourth one, thermal plasma oxidation of metal foils. Where I want to discuss metal oxide nanowire. In this, a schematic of typical horizontal quartz tube reactor used for the catalyst assisted synthesis of nanowire has been shown. Many of the catalyst assisted synthesis techniques for metal oxide nanowires use thermal CVD in a quartz tube reactor as shown in the schematic. This setup includes a horizontal tube heated with a two-zone furnace with one zone for evaporation of solid metal sources and another zone for growth on substrate coated with catalyst layer. The chemical vapor deposition, which is known as CVD, of metal oxides when performed on substrates coated with a thin film or layer of catalyst particle can lead to metal oxide nanowire growth with catalyst particles as their tips. However, the metal containing gas or liquid precursors are not readily available for deposition of many metal oxides. So, it is easier and inexpensive to start with either solid metal or metal oxide powder sources. The catalyst is typically deposited onto substrate as a thin film less than 100 nanometer thickness, either using sputtering or evaporation. In some cases, dispersion of catalytic particles can be synthesized or purchased separately and spin coated onto the substrate. Where I want to discuss the direct oxidation of large molten metal droplets to form metal oxide nanoparticles. Another method which is being frequently used for this growth of nanowire is direct oxidation scheme using low melting metals, which is shown in the figure. The synthesis procedures involving direct oxidation of metals are gaining importance compared to catalytic assisted growth method, mainly because of these two reasons. The first one, a possible contamination with foreign catalyst metal in the catalyst assisted growth, and the second one is the cost associated with respective catalyst metal and corresponding processes. The solubilities of oxygen and the respective oxide in the low melting point metal melts are expected to be negligible. So, any amount of dissolution of oxygen species during direct oxidation of large micron-scale molten metal droplets lead to spontaneous nucleation of nanometer-scale metal oxide nuclei with molten metal. Further, growth of metal oxide nuclei via vessel attachment lead them to one-dimensional structure. High density of nucleation followed by growth via vessel attachment from large molten metal clusters result in flowery morphology in which a high density of nanowire emanates from one point. After nucleation stage, further growth of metal oxide nuclei can also occur laterally in addition to vessel growth. Such growth behavior lead to polycrystalline crust formation on large molten metal clusters. It has been found that the presence of reducing species such as hydrogen or chlorine reduces the lateral propagation of metal oxide nuclei. This is schematically illustrated in the figure. A chemical vapor transport of high melting metal oxide will be discussed. Chemical vapor transport of high melting metal oxide is another growth technique for obtaining the nanowires. In the case of high melting point metals, for example, tungsten, tantalum, and molybdenum, their melting points are always much higher than the synthesis temperatures in most of the procedures. For such metals, the respective oxide vapors can easily be produced through oxidation of the corresponding metal at temperatures much lower than their melting point of metals. The transport of the respective metal oxide vapors onto the substrate can be used to create metal oxide films similar to any CVD technique. However, it has been shown that under particular circumstances with low oxygen partial pressure, such chemical transport procedures results in the synthesis of respective oxide nanowires without the aid of any external catalyst. Such a scheme can be appropriately desired as vapor solid since the respective metal is not molten at the synthesis temperature. A scheme of hot wire CVD reactor setup used for chemical vapor transport experiment using a variety of high melting point metals as filaments has been shown in figure. In brief, the hot wire or filament CVD experiment can be conducted using oxygen flow over tungsten filaments for the synthesis of tungsten oxide nanowires. As shown in figure, the reactor consists of 2-inch diameter quartz tube with the metal filaments wounded on top of 2 ceramic tubes which are connected to an electrical feed through. The filaments is resistively heated by flowing electric current and the temperature is controlled by controlling the applied power to the filament using a variac power supply. The quartz tube is placed inside the furnace oven. In addition to the oven, the radiation from the filaments can heat the substrate to high temperature depending upon their distance from the source. The substrate can be easily heated up to temperature around 5 to 550 degrees Celsius in 2-inch quartz tube without the use of external heating via furnace. Experiments using tungsten filaments and oxygen flow at low partial pressure in the range of 0.05 to 0.3 torr, filament temperature around 1600 degrees Celsius and substrate temperature around 500 to 800 degrees Celsius result in the synthesis of tungsten oxide nanowire. So students, let us now summarize what we have learned in this module. We have learned the quantum confinement from two directions lead one-dimensional nanostructure known as nanowire. Growth and advantages of semiconducting nanowires, silicon nanowires, germanium nanowires has been studied. Group 3rd and 5th based nanowire such as gallium arsenide, indium selenide, indium phosphide, their synthesis, novelty and application has been discussed in detail. Various synthesis methodology for the growth of metal oxide nanowire such as catalyst assisted growth, direct oxidation of large molten metal growth, direct chemical vapor transport or CVD method, and thermal plasma oxidation of metal foil has been studied. Thank you.